Welcome everyone. In this video, I will be covering section 16.2, line integrals. In this section, we define an integral that is similar to a single uh, variable integral, except that instead of integrating over an interval a to b, we integrate over a curve c. Such integrals are called line integrals, although curve integrals would be a better terminology. They are used to solve problems involving fluid flow, forces, electricity, and magnetism. Let's first write the definition of line integral. Write the definition of line integral of a scalar function f. Note, here we are going to do scalar function. The next we will be defining line integral for a vector function as well, for a vector field, along a smooth curve C with respect to the arc length. So we are writing down the definition of a line integral for a scalar function, lowercase f, along a smooth curve C with respect to the arc length. If C is given by the parametric equations, x equal to x of t, y equal to y of t, and t lying between a and b, we divide the parameter AB into n subintervals ti minus 1 ti, as shown here in this picture, of equal width. The ith subinterval corresponds to the subarc of C with length delta Si. So in this picture, you notice um, this t is the parameter. This t is the parameter. Parameter runs from A to B. Then within that in A to B, there is a curve shown in pink. And you're dividing AB into number of subintervals of equal width. We are looking at the ith subinterval from Ti minus 1 to Ti. So we are looking at this ith subinterval and the corresponding arc, which is from Pi minus 1 to Pi. The generic point on that arc is Pi star, Xi star, Yi star. Then the line integral over C, f of xy ds, so lowercase f, that's important here, f of xy ds stands for the arc length. First, we will write down in terms of Riemann sum, the limit as n approaching infinity, sigma, I varying from 1 to n, f of xi star, yi star, delta Si. So if you notice here this particular definition in Riemann sum, so you have a curve that is shown in pink. Above that curve, you have the surface. You are multiplying the height at that point f of xi yi, which is f of xi yi is the height at the point xi yi. You are multiplying by the length. So height multiplied by length gives you the area. So it's like you have a curtain above this curve and you're looking at the area of one side of the curtain. Just as for the ordinary single integral, we can interpret the line integral of a positive function as an area. In fact, if f of xy is more than or equal to 0, then integral over c f of xy ds represents the area of one side of the fence or curtain, as in this figure, whose base is c and whose height above the point xy is f of xy. So just in the Riemann sum, if you just look at this little piece, a little piece over here, it's kind of a rectangle, and this piece is delta Si piece, and this height is f of xi star or f of xi yi. This being the first subinterval, you can call it f of x1, y1. So you are multiplying the height by the width, so that becomes the area. And you are doing this for every sub-interval, sub-arc. So you get number of rectangles like this. That becomes a Riemann sum. Riemann sum always can be translated into integral. So we have integral over C, f of xy ds is the line integral with respect to the arc length. How do you evaluate such a line integral? Integral over C f of xy ds can be written as integral a to b, where a and b are the endpoints of the parameter t. Imagining that we are writing x and y in the form of parametric representation, x as a function of t, y as a function of t runs from a to b. So you have f of x of t, comma y of t. Then we have that ds, which is the arc length. So from earlier, from parametric chapter 10, we know that it is dx by dt, the whole square, plus dy by dt, the whole square, dt. And you know that this representation you have done, the length of the arc in both in chapter 8 and chapter 10. In chapter 10, you saw the parametric representation. So this is more of chapter 10, finding the arc length. So the ds part corresponds to the square root along with the dt. That is the arc length. Similarly, if C is a smooth space curve, instead of um, any curve, if it is a space curve, then it will be three-dimensional. Then integral over C f of x, y, z ds would be extending the previous idea for two. You have f of x of t, y of t, z of t. Then the arc length part, which is dx by dt, square root of dx by dt, the whole square, dy by dt, the whole square, plus dz by dt, the whole square, dt. The arc length, ds, all of this. Observe that the above line integrals can be written in vector notation in a simpler way as follows. Integral over C f of xy ds in um, vector notation can be written as integral a to b, which are the bounds of the parameter t, f of r of t, which is the space curve, times absolute or length of r prime t dt. You have seen in chapter 13, if you refer chapter 13, you will see that ds, the arc length corresponds to absolute r prime t, length of r prime t dt. It is the velocity vector, and you take the magnitude of the velocity vector, that will be the length. Derivative vector. For the special case f of xyz equal to 1, we get integral over c ds. So here the integrand equal to 1. So we'll have this part is equal to 1. So it is just integral a to b absolute length of r prime t dt. Length, it is the first derivative, absolute r prime t dt, integral a to b. That is nothing but the length of the curve. Again, this idea was explained in chapter 13. So if the height of the curve, if the height f of xy is taken as 1, then this integral over c ds, the line integral value will become just the length of the curve because of this definition here. Where L is the length of the curve C, note that f is a scalar function. So in this section mainly, you may want to clearly understand, because later on in the same section we will be deriving, we will also be defining the formula for line integral for a vector field. This part, how to evaluate line integral for a scalar function, and this formula for 2 dimension and 3 dimension, and how you go from the line integral definition to the arc length, you need to know this paragraph. And problem number 3 and a few other problems are done in the section videos. Problem number 15, 21, 39, 39. All these are done in the videos for the section. Please refer to them. Line integral. This particular video is part A of concept video on section 16.2. We will be continuing with the rest of the material in this section in part B of the concept video of section 16.2. Please make sure to watch part B of the video as well for this section. Hope this video helps.